Now we're going to move in this lesson to three-dimensional coordinate systems and vectors in three-dimensional space.
I am so glad.
I'm so ready.
I can't wait.
Well, I'm glad to hear such enthusiasm. So, if we have a three-dimensional coordinate system, I drew a picture here. The dotted lines represent the negative, like this is the negative z-axis, the negative x-axis, and the negative y-axis. If you can see the little x, y, and z there. If you can imagine, the xy plane is this one, and then the z-axis kind of comes out of the intersection of the x and y-axis at the origin. Things to be aware of: z comes out this way, forming what's called a right-hand triple. And if you can imagine holding up your right hand and looking at the position of your index finger, middle finger pointing at you, and your thumb, that's a right-hand triple. If you held up your left-hand triple, a left-hand triple would be like this, except the negative z-axis would be up here and the positive z-axis would be down here. That would be what's called a left-hand triple. And so if you think about your axes forming a right-hand triple, you've got it. So anyway, sometimes I'll abbreviate this whole thing as r cubed, which means three-dimensional space, right? Because there's three real axes there defining three-dimensional space. And a point has coordinates like this: x, y, and z, sometimes called an ordered triple as opposed to called an ordered pair. X is the shortest distance to the YZ plane, Y is the shortest distance to the XZ plane, and Z is the shortest distance to the XY plane. So the coordinate axes in standard position form a right-hand triple. I already said that, didn't I? So if your head is going along the positive Z-axis and your arms are the X and Y axis respectively, you are forming a right-hand triple when your right hand is the X-axis and your left hand is the Y-axis. Okay? Can you picture that right here? Your head is here, your left hand's the Y-axis, your right hand's the Z-axis. And if you were standing, if you're upside down, see, that would be a left-hand triple. You know, if the Z was turned this way. So, for a left-hand triple, put the x-axis along your left hand. If you switch the positions of the x and y-axes, that would also make this a left-hand triple. Okay, so the ordered pair, or the ordered triple, I should say, the point 2, 3, 2, 5, negative 3 would be in what place in this three-dimensional space? Well, x is 2, so I'd count out here 2 units. Y was, I forget, 5. So I count out here 5 places, so I'm out here 2, out this way 5, and then Z was negative 3, so I drop down 1, 2, 3 units. Okay, I think I have that pictured in this drawing right here. See, 2 units of X, 5 units of Y, negative 3 units of Z, and then that would be the point and the position of that ordered triple. To figure out how to find the distance between points in space, we want to know the distance between x1, y1, z1 and x2, y2, z2. Aha! Sounds familiar, doesn't it? So the projection both points make onto the xy plane, we'd make both values as e0, would show the distance between the projections is the same as the usual distance formula, right? Square root of x2 minus x1 squared plus y2 minus y1 squared, right? If you can imagine taking your 2 points and project them into the xy plane, then the distance between them would just be the normal thing, because both z's would be 0. But then we want to find the distance between the points. That actually, if you think about it, that would give us a line in the plane of the lowest z that then we could use as one of the sides of a right triangle, and then use the side to the higher z to the other as the three sides of a right triangle, and then use this distance, square root of x squared, or square root of x2 minus x1 squared plus y2 minus y1 squared, and then this one is just z2 minus z1 squared. But by the way, these square roots, of course, you got to square that and then take the square root of the whole mess. So if you're finished with that, you should be able to see that the square of the distance is this, right? That's in the xy plane, and then this would be the difference between the z values, okay? And so then if you square a square root, you just drop the radical, so d squared is x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. But then we want the distance, not the square of the distance, so we take the square root of all that mess, okay? So let's do the example in the next video.